So this paper grew out of a question that I had. There was a paper published by Shripad Tuljaperkar. There was a paper published by Shripad Tuljaperkar in the Proceedings of the National Academy of Sciences in 2018, and he showed that there was an advancing frontier of deaths. And he said that there appeared to mainly be mortality postponement. And by mortality postponement, what we mean is that the maximum age of death is actually rising. And I had a paper with a former PhD student where we used a Gompertzian approach similar to the one I'm going to talk about now. And we looked at cohort data going back to 1760 or so in Sweden. And we found that over that recorded period, the vast majority of changes in longevity had in fact been due to mortality compression. And mortality compression is where the maximum age doesn't change, but as mortality improves, deaths bunch increasingly closer towards that maximum age. And so this paper grew out of a question I had about whether these two papers or these two findings could be reconciled. So if I press that, I should get... So quickly what we do is we analyze historical changes in period data. So Shripad Tulja's paper used period data. Our paper used cohort data. And so what we did was we analyzed it in the context of the Gompertz law, which I'll talk about now. We found that the Gompertz law has become an increasingly poor fit, and there seems to be the shifting of some deaths from the 7th and 8th to the 8th and 9th decades of life, but that improvements in longevity have been due to a mixture of compression, postponement, and this growing Gompertzian error, which we think is largely compression, and that this improved old age longevity has indeed increased retirement savings targets, but what's also happened is that because a large fraction of that improvement in longevity is due to compression rather than postponement, this has actually reduced the risk caused by uncertainty in the length of life in those savings targets in both absolute and relative terms. So just a very quick background, that's what the human mortality curve looks like. So on the vertical axis, I've got a 1-year probability of death, and on the horizontal axis, I've got age, various features, high birth and infant mortality, a lifetime low around age 9, they're the so-called accident humps, and then from around age 40, there's what's called senescence, i.e. the process of growing older, and you can see on that graph it's broadly a straight line, and that is called the Gompertz law. So Benjamin Gompertz in 1825 first discovered that mortality at older ages at least seems to rise exponentially with age. It's a straight line here because it's on a log axis. I've plotted lines on that graph, and you'll see that those lines sort of match old age mortality very well, and they meet the lifetime low mortality around at the low around age 9 again. And this sort of raises an interesting point about whether the senescence actually starts much earlier, may start around age 10, but in fact the reason that we see mortality that's different from that is because of unnatural deaths of young males and young, to a lesser extent, young females. And so the working assumption that we adopt in this paper is that in fact the Gompertz law of senescence is in fact the natural pattern of aging, and there seems to be some indicative support for that hypothesis. Importantly, what I want to emphasize is that here I'm using period data, and for those of you who aren't mortality fundis, it's important to understand the difference between period and cohort mortality. So period mortality is the mortality of a particular population in a particular year, and that is there. I've got the US in 2000, those are the solid lines. But those are not the mortality rates experienced by any individual. They're theoretical constructs, and because individuals move through time, we age through time, and so that means that the generation of 1910, for instance, had mortality at age 50 that was higher than the generation of 1950. And so if you plot the mortality experience of real people, you get what's called a cohort mortality curve, and that is the dotted line. And because over this period between 1960 and 2010, the mortality has improved, the actual slope of the line, it's still a straight line, is still a pretty good fit. But what happens is that as mortality improves, the slope of that line is slightly shallower than the slope that you will observe in a period table. And so the generation of 1910 had low mortality at 100 than the generation of 1900. And so you can see that the two curves intersect at age 90 because the generation of 1910 was 90 in 2000, but it has a slightly shallower slope. And that has important implications for what I'm going to talk about. So that's a mathematical expression of the Gompertz law. It captures broad features of the shape of the mortality curve above age 50. It fails at very high ages, probably due to differential frailty within each cohort. So what that means is that at very high ages, say 100 or higher, that linear increase starts to look a little bit more sublinear. And in fact, there is some evidence, admittedly contested, which suggests that when you reach a certain level of mortality, around 2/3, and so that corresponds to an annual probability of death of around a half, mortality rates may even plateau with age. So what we did in our paper was we used the Gompertz law to divide changes in mortality between compression and postponement. And so you can imagine that you've got this straight line of mortality which reaches this height of 2/3 or log of 2/3. And then you're comparing two groups of people, and you want to divide the entire mortality curve between a portion that's due to mortality compression and a portion that's due to mortality postponement. And what we decided to do was to say the changes in the intercept are mortality compression, because that will cause an unambiguous concentration of the age at death, just at ages below the Gompertzian maximum age. And then changes in the slope are mortality postponement, because that will cause an unambiguous increase in the variance of age at death. And so what we did in this paper is we fitted the Gompertz law to mortality rates over 50, to period population mortality rates from the HMD, roughly the period 1960 to 2020. We subtracted 1 year because of COVID. So we looked at 1959 to 2019 because we didn't want 2020 to, which is hopefully temporary, to bias our results in any way. We then calculated measures of interest. So we looked at the mean age at death, the percentiles of the actual and fitted age at death distribution, and the Gompertzian maximum age, which is when that mortality rate first reaches 2/3. And then we disaggregated changes in these measures of interest to changes due to compression, postponement, and the Gompertzian error. And so there you can see the graph, the table, sorry. And you can see that without putting too fine a point in it, the intercept does indeed fall, and this is US males, and the slope rises. And then the question, of course, is the slope rising more or less than would be consistent with pure compression? And in fact, you can see that between 1959 and 1989, in fact, there was barely any change in the Gompertzian maximum age, which suggests that these changes here are mainly due to compression. For females, it's a slightly different pattern. The Gompertzian maximum age rose from around 104 to 107, and then even further to 109. So for females, there is indeed some compression, but there's also some postponement over the whole period. And for males, there was a substantial amount of postponement in the last 20 years, so between 1999 and 2019. So this is what the fitted and the actual mortality rates look like. And you can see that firstly, there are errors in recording ages. So people notoriously lie about their ages. When you're younger, you tend to lie downwards. But when you get very old, then it seems that you start to lie upwards. And I guess reaching age 100 is such an achievement. You say, yeah, well, I'm 110. So those those really predate the introduction of comprehensive birth registration in the United States. So we can treat those with some degree of skepticism. There's a British demographer, Saul Newman, who's looked at supercentenarian mortality, and he says that the biggest impact on supercentenarian mortality was the introduction of comprehensive birth registration. So let's treat those with some degree of skepticism. But there are some important features in this graph that are worth noting. And the first is that the Gompertz law fits earlier cohorts very, very, very well. And you can see that, in fact, there's a straight line. It fits the straight line very well. Then there's that leveling off, okay, and then these errors. But what happens over time is that the Gompertz law seems to become an increasingly poor fit. And so we have this over-prediction of mortality rates at these ages, and an under-prediction of mortality rates at those ages, and then that leveling off at around log of 2/3, which is minus 0.4 or thereabouts. And so it looks like what's happening is that there's some intervention. If you take this hypothesis that the Gompertz law represents some natural mortality, then there's some intervention that's becoming increasingly important that is shifting deaths from ages 70 and 80s to 90s and beyond. And because this does not seem at the moment to be increasing the maximum age at death, you can regard this as compression rather than postponement. And here's the theoretical distribution of the age at death, and you can see that a very similar pattern obtains. You've got it fits, the Gompertz law seems to fit young and old ages very, very well, but in the middle, it's becoming an increasingly poor fit over time. And so what we did was we then calculated these measures of interest, and you can see that basically what's happened is that there's been, and here I've got the median age at death, 75th, 90th, and 95th percentiles, and I've divided the changes between compression and postponement. An important question, though, is what does this mean for a successful retirement? And so what I did was I calculated a consumption-based measure of savings adequacy at retirement. So if you wanted to plan for retirement, how much would you need to save as a multiple of your consumption? So I'm not looking at income, I'm looking at consumption. And you can see here that for a US male who had mortality equal to the US population, aged 50, and they wanted to be 95% certain they would have enough money, they would need to plan for living another 45 years. And in fact, for a female person who had mortality equal to the US female population, aged 50, and they wanted to be 95% certain that they would be okay, they would have to plan for another 48 years. So it's a substantial amount of risk, because there's a big difference between the median and the 95th percentile. So this savings target measures the multiple of consumption required, and I used age 67 in the paper, there are other ages, to meet your lifetime consumption at each percentile of the age at death distribution without taking any investment risk and assuming that Social Security covers 30% of your retirement needs. So the best way to look at these is, this is an older version of the slide, but I had a graph. But basically the idea is that, and these are after-tax numbers, so if you want to think about this in terms of a pre-tax account, if you want to be 95% certain that you're going to have enough assets to sustain your consumption, you would need to have assets equal to 14 times your annual consumption, and if your marginal tax rate in retirement is 20%, you'd have to divide that number by 1 minus 20%, which is 0.8, so you would make that more like 17. And so, and so what's happened is that over time, at 50, the median has improved dramatically, but the difference between the 95th percentile and the median has actually shrunk, both in absolute and in relative terms. And so what's happened is that although this, and the reason for that is because a large portion of the longevity improvements are in fact due to mortality compression rather than mortality postponement. And so then the final question is, what is the future going to look like? And of course, the future is very hard to predict. But my guess is that what's going to happen is that mortality, the US has, in the medium term, the US will probably end up looking like Europe, which is slightly ahead. In the very long term, as medical science targets aging rather than the symptoms of aging, we may expect mortality postponement to become more important, and that will cause the risk in these retirement targets to actually increase. So thank you very much.